Life on Earth is all because of light. Plants prepare their food by the process of photosynthesis. Photosynthesis requires water, chlorophyll, carbon dioxide, and sunlight. Human beings and animals eat plants and animals to meet the energy requirement for life. In the absence of light, no photosynthesis, no plants, and no life. Well, in this program, we shall discuss the phenomena of reflection, refraction, diffraction, interference, and polarization. Just in the end, we shall have a brief view of different theories of light. Optics is the study of light and its propagation through various materials. Traditional application of optics includes lenses for vision and image formation by telescopes and microscopes. Modern application includes information storage and retrieval, such as CD player and signal transmission through optical fiber cables, which carry a greater density of information than copper wires and are lighter in weight and less susceptible to electronic interference.
The function of a wave is to carry energy from one point to another point. Now look here. When I move my finger up and down here, you can see the movement in the piece of paper. I haven't touched this piece of paper directly, so how it moves? Actually, I imparted energy here, and the water waves has carried this energy from this place to this place. Can I transfer this energy from this place to this place without water? Of course not. So the waves which require certain medium for their propagation are known as mechanical waves. Can we talk to each other in space? Of course not, because we require certain medium for the sound waves to travel from one place to another place. So the sound waves are also mechanical waves. There is another kind of wave known as electromagnetic waves. The waves which do not require any medium for their propagation are known as electromagnetic waves, like gamma rays, X-rays, ultraviolet rays, light rays, radio waves, and microwaves. The third kind of waves are known as matter waves. These are the waves which are associated with the motion of subatomic particles like electrons and protons.
The set of these electromagnetic waves is termed as electromagnetic spectrum. What distinguishes light rays from other electromagnetic spectrum is that we have receptors. Our eyes that are sensitive to electromagnetic radiations only in narrow range of wavelengths from 400 nanometer to about 700 nanometer. Can we see light? Moon reflects sunlight to Earth. We cannot see incident and reflected light. We can only see the moon upon which the light is being reflected. Look at this incident. Reflection of light was minimum and the man could not see the glass. When light rays moving through medium first strikes at the surface of medium second, then part of the light rays is reflected back into the same medium first. It is known as reflection of light. The parts of light ray which enter into the second medium is called refracted light, and we call this phenomenon as a refraction of light.
When light passes through a narrow slit or by a sharp edge, it always bends around the corner. This phenomenon is known as diffraction of light. Diffraction is also observed in other waves like sound waves and water waves. We can demonstrate the phenomena of diffraction with the help of ripple tank experiment. Now watch here. Here we have a source of plain water waves. This is the source of plain water waves. And here we have a very wide slit. Now the plain water waves will pass through this wide opening, and we will not get any diffraction effect on the screen. You can see here the plane waves passes through without any diffraction. Now I decrease the width of this slit. Now watch this. we can see that the water waves bends around the corner in this case. So the necessary condition for the diffraction is that the size of opening should be comparable to the wavelength of the wave used. This is the necessary condition for diffraction. If we want to have diffraction in light, then we must have a narrow slit so that the size of the slit should be comparable to wavelength of light, which is of the order of 6 into 10 raised to power minus 7 meter.
In this scene, Group A standing in this corridor can hear the voices of Group B on the other side of corridor, but cannot see one another unless they move and change their positions. Can you give a scientific answer? The wavelength of sound wave is comparable with size of edge, so the sound waves diffract and reach these people, whereas light waves have shorter wavelengths and cannot bend or diffract at this edge.
When two waves which are in phase coherence superimpose on each other, then either they cancel the effect of each other or reinforce the effect of each other. We call this phenomena as interference of waves. If the two waves cancel the effect of each other, then we call it destructive interference, and if they reinforce the effect of each other, we call it as constructive interference. We can demonstrate this phenomena with the help of this ripple tank experiment. Here we have a source of water waves. Now these water waves which are produced as a result of up and down motion of my finger, these two waves after passing through the slits either produce constructive interference or destructive interference. Now the bright bands on the screen, now you can see the bright bands on the screen. The bright bands on the screen are due to constructive interference, and dark band on the screen is due to destructive interference. There are certain conditions for interference. Here we have two sources of water waves. The two sources are close to each other, so the resulting water waves can superimpose and we can get bright or dark regions on the screen. On the other hand, if I take one source here and other source here, now the two sources of water waves are very far away from each other and the resulting water waves cannot superimpose, so we will not get any interference effect on the screen. So the first condition of interference is that the principle of superposition must apply. The second condition of interference is that the sources should be monochromatic. This means that the two waves should have the same wavelength. If this condition is satisfied, then we will get interference pattern on the screen. Failing to this condition, although we will have interference effect, but we will not be able to get stationary interference pattern on the screen. The third condition is that the two waves should be phase coherent. Now look this motion or this motion. The two sources have certain phase relation with each other. We say that the two water waves which are produced as a result of this vibrational motion are in phase coherence. On the other hand, watch this haphazard motion. Now the two sources are not in phase coherence and we will not get any interference pattern on the screen. So the third condition is that the sources must be phase coherent.
If light behaves as water waves, then light rays from these two bulbs should either interfere constructively or destructively, depending on the power difference at different points on this screen. We expect dark and bright regions on this screen. Look at this screen. We do not observe any dark or bright regions here. Should we conclude that no interference effect takes place in light? Certainly, it is not the case. Light is emitted as a result of vibrations of atoms of filaments, and these atoms of two sources do not act together in a cooperative way. This means that light of these two sources is not in phase coherence. Thomas Young solved this problem of phase coherence in 1801. He used a single source of light. The light, after passing through this slit S0, bends around the corner due to diffraction and falls on these two slits S1 and S2. Now the light rays coming out of these two slits are in phase coherence because they are coming from the same single source. Now, the condition of interference is satisfied and we observe the interference effect on the screen.
In order to analyze the interference pattern, we consider light waves from each slit S1 and S2 that combine at arbitrary point P on the screen C. The point P is at a distance of R1 from slit S1 and R2 from slit S2. We draw perpendicular S2B on line S1P so that PS2 and PB has equal lengths. Angle S1, S2B is theta. D is the distance between slits S1 and S2 called slit spacing. D is the distance between center of two slits and center of screen. Convex lens is used to focus the light rays from S1 and S2 at point P. The lens should be placed at distance equal to its focal length f from the screen. Y is the distance of point P from the center of screen O. Please note that distance S1b is the extra distance which light ray from S1 covers as compared to S2, and we call it as path difference. Now consider right angle triangle S1, S2b. We have sine theta is equal to perpendicular over hypotenuse. Sine theta is equal to S1b over d, or S1b is equal to d sine theta. For point P to be on right region, the path difference should contain a whole number of wavelengths. So S1b is equal to m lambda, where m is equal to 0, 1, 2, 3, and so on. As S1b is equal to d sine theta, that implies d sine theta is equal to m lambda. If distance between screen B and C is much greater than the distance between two slits and point P is close center of screen, then we can use the approximation sine theta is approximately equal to tangent theta. Now from the triangle PQO, tangent theta is equal to y divided by d. So that sine theta is equal to y divided by d. Now d sine theta is equal to m lambda, which implies that d into y over d is equal to m lambda. So y is equal to m lambda d divided by d. Putting the values of m is equal to 0, 1, 2, 3, and so on, we get different values of y as y is equal to 0, lambda d over d, 2 lambda d over d, 3 lambda d over d, and so on. At these distance from the screen, we have bright bands. Now look at this situation. Here you can see the path difference d sine theta is equal to 1 wavelength lambda, and the two waves arrive at point P in phase. Point P will be on right region due to constructive interference. Now watch this situation. Here we see that path difference d sine theta between the light rays from S1 and S2 is equal to half the wavelength. The two rays arriving at point P will be at dark region due to destructive interference. Thus, we conclude that condition for destructive interference is d sine theta is equal to m plus 1 by 2 into lambda, where m is equal to 0, 1, 2, 3, and so on. Again, sine theta is approximately equal to tangent theta is equal to y divided by d. That is, d into y over d is equal to m plus 1 by 2 into lambda. That implies y is equal to m plus 1 by 2 into lambda d divided by d. Putting the values of m, which is equal to 0, 1, 2, 3, and so on, we get y is equal to 1 by 2 lambda d over d, 3 by 2 lambda d over d, 5 by 2 lambda d over d, and so on. This means that at these distances from point O, the screen will be on dark regions. You might have seen colors in a soapy water film on a wire loop. The black segment at the top is not a torn film, but it is because of destructive interference of light from the front and back surface of the thin film. Newton's rings are the result of air film of increasing thickness between plano-convex and plain glass plate.
Dear students, you have already learned that interference occurs when two waves of equal frequencies and equal wavelengths overlap at a point after they have traveled through different paths. The waves of equal frequencies and equal wavelengths can be obtained by splitting a monochromatic beam of light in two parts. The components are made to travel along different paths, recombine, and produce interference. A Michelson interferometer ingeniously applies this principle. It is used for accurate measurement of wavelength, accurate measurement of length and thickness of transparent plates. It consists of a source of monochromatic light, two glass plates of exactly equal thickness and of the same material fixed on a metallic frame inclined at 45 degrees to the direction of incident beam. Two mirrors, one of them is fixed with the frame and the other is movable. When a beam of light enters this glass plate G1, it is partly reflected and partly transmitted at the back surface. The reflected beam passes through this glass plate G1 and moves on to this mirror M1, and the transmitted beam moves to the other mirror M2. They are reflected back, retrace their path, and finally recombine to produce interference. When mirror M1 and M2 are in exactly perpendicular planes, circular dark and bright fringes are observed through the telescope.
The experiments on interference and diffraction have shown that light is a form of wave motion. The phenomenon of polarization tells us that light is transverse wave. A wave in which particles of the medium vibrate in a direction perpendicular to the motion of wave is called transverse wave. Light emitted by a source has all directions and is called non-polarized light. When a polarizing sheet P1 is placed in the path of light rays, only those directions of light vectors are transmitted which have their axis parallel to the axis of polarizing sheet. The light rays after passing through polarizer is plane polarized. If the axis of analyzer sheet P2 is parallel to polarizer, then the plane polarized light will also pass through P2. Now rotate analyzer P2. The light will become dimmer and dimmer, and no light will be observed when axis of analyzer P2 becomes perpendicular to polarizer P1. Polarization has many applications. The reflected light from roads and lakes is linearly polarized in horizontal plane, so we use sunglasses with optical axis vertical. In this way, the horizontally polarized light cannot go through. The headlights of vehicles are made up of crystalline glasses to form beam of light in one direction. The curtainless windows cut most directions of light vectors, and only specific directions of light are allowed to transmit. So, the direct sunlight is avoided.
Until the beginning of 19th century, light was considered as stream of particles. The main architect of this theory was Newton. He explained reflection and refraction on the basis of this theory. In the lifetime of Newton, another theory was put forward, which we call wave theory of light. According to this theory, light is a kind of wave motion. In 1678, Huygens explained the laws of reflection and refraction on the basis of this theory. Wave theory of light did not receive immediate acceptance due to several reasons. Number one, all waves known at that time were mechanical in nature, like sound waves, water waves. Now, light travels from sun to earth through vacuum. The question is how it happens. The second main objection on this theory was that if light is a kind of wave, then it should diffract and we should see around the corner. Also, light should exhibit interference effect. No such evidence could be provided at that time. Later on, in 1801, Young, with the help of his double slit experiment, demonstrated for the first time the phenomenon of interference of light. Augustin Fresnel, several years later, performed number of experiments dealing with the interference and diffraction of light. In 1865, Maxwell showed that light is a kind of electromagnetic wave, which means that light does not require any medium for its propagation. But unfortunately, this electromagnetic theory of light could not explain photoelectric effect. What is photoelectric effect? When ultraviolet light is made to fall on metal plate, electrons are emitted. These electrons are known as photoelectrons, and this phenomenon is known as photoelectric effect. Max Planck was a scientist who was working on heat radiations. He said that heat radiations are not continuous, but consist of packets of energy called photon. Einstein took the idea of Max Planck and said that not only heat radiations, but all kinds of radiations like light consist of these packets of energy, which we call photon or quanta. This theory of light is known as quantum theory of light, and Einstein successfully explained the photoelectric effect on the basis of this theory. Now the question is, which theory is correct, quantum theory or wave theory? The answer is, both are correct. When light exhibits particle nature, its wave nature becomes absent. And when it exhibits wave nature, its particle nature becomes absent. It is just like a coin. Either you can see head or tail. You can't see both simultaneously.
Well, to summarize the program, we learned about reflection, refraction, diffraction, interference, and polarization, and different theories of light.